Okay. Perfect. We are online, so I think that we can start. Good morning and welcome everyone to the webinar Atmospheric Chemistry and Physics, Ozone. I'm Monica Proto, technologist at the National Research Council, and I'm very pleased to welcome you and moderate this webinar. I'll spend just a few words about the purpose of the webinar and some technical indications. The today webinar is the first of three arranged by the National Research Council in cooperation with the European Centre for Medium Range Weather Forecasts and the Copernicus Climate Change Service. The webinars are focused on the use of in-situ climate data and to provide information on the use of them, on their measurement, and finally their application. A wide range of data and services have already been provided under the Copernicus contract for the implementation of the C3S Climate Data Store. I would like to thank all participants for attending this Copernicus training activity, and where I'm so honored to introduce the two speakers who are the two renowned international scientists. I thank you both for accepting with enthusiasm and dedication our invitation to take part to this event. Welcome to Martine de Mazière. She is acting director of the Royal Belgium Institute for Space Aeronomy since June 2011. Her activities at PIRAIASO have been focusing on remote sensing of the atmospheric composition from ground and space using infrared spectrometry. In the last decade, the focus has shifted to climate pollutants and long-lived greenhouse gases. She and her team contribute to the Copernicus services and international monitoring networks and European research infrastructures, ACTRIS and ICOS. Martine de Mazière has been co-chair of NDAC since 2013. Now welcome to Betsy Weatherhead. She is an atmospheric scientist specializing in climate observation. She is a fellow at Jupiter Intelligence, where she works with groups internationally to address climate justice and improve understanding of how the Earth is changing. She has been working with the Copernicus Climate Change Service since 2017 to help assure the quality of climate data. She was an early advocate for advanced statistical techniques, citizen science, and new observing techniques, including the use of autonomous vehicles. Now, the presentation will be jointly led by Martine and Betsy. Please, I invite who would like to submit their questions to the speakers to write their questions in the chat box. Should you have any comments or some highlights you would like to add, please don't hesitate to write them as well, because at the end of their presentation, the speakers will spend some extra time to answer. Finally, I want to remind you that the webinar will be recorded and made available on the C3S webpage. Now, I leave the floor to Martine and Betsy. Please, we can start. Thank you.
Thank you, Monica. This is Betsy Weatherhead here. It's a pleasure being able to present with Martine. We are going to cover a number of issues with respect to ozone, but we both want to make it very clear that there's no way that this presentation could be comprehensive. So instead, we're going to be covering some of the highlights of the use of in situ and ground-based observations, what has happened in the past, where the focus is today, and where we see the work going in the future. So again, we aren't going to be comprehensive, and at the end, in addition to questions, we welcome comments and other thoughts from ozone scientists and climate scientists who have chosen to join us today. Okay, so here is the rough outline of what we're going to cover. Give the very basics about ozone in the atmosphere, and then Martine is going to go into some real detail about how we do the in situ and ground-based measurements of ozone. We'll cover some issues with respect to ozone variability and the long-term changes we're seeing. Then I'll be talking about some of the international legislation that's taken place with respect to ozone, and that legislation has been extremely successful. We're going to talk about how and why it has succeeded. We're going to go on and talk about the interplay between ozone and climate change. And then we're going to offer some of our thoughts on what is left to understand and the lessons we have learned from ozone. So, ozone in the atmosphere. Ozone is a very small part of the atmosphere. I think as most people on this, listening to this presentation will understand that the bulk of the atmosphere really is nitrogen and oxygen and CO2, with ozone being a very small part. It's a very small part of the atmosphere, but it's a very powerful and very important part of the atmosphere. I hope people are aware that ozone is really 3 oxygen atoms together, whereas the typical oxygen that we breathe is 2 oxygen atoms that we put together. An understanding of ozone really started in the mid-1800s, where it was studied by some Europeans, Schoenborn, Ozone, Sorey, in around the mid-1800s. And then there was an enormous amount of research that took place after 1930s. This focus was on both surface level ozone and total column ozone. But I want to be clear, even if humans have only been really focused on ozone for the past, say, 180 years or so, ozone has been a part of our atmosphere for as long as oxygen has been in our atmosphere, at least 3 billion years or so. And we know this from a variety of sources: ice cores, oxygen isotopes, fossil records, etc. But particularly the records of plants can give us estimates of ozone levels going back thousands of years and even billions of years. Even just going back a few thousand years, we can understand that ozone has been a stressor for human beings. For instance, in the Arctic, snow blindness, which is still a common cause of human irritation and real problems today. Snow blindness is 100% a UV effect, and the Arctic is the only place that I'm aware of where protection was designed to help us protect our eyes against UV radiation. It wasn't necessary in the tropics, but it was necessary in the Arctic region for the last several thousand years. So again, we have multiple lines of evidence that let us know that up until the Anthropocene, up until the last few hundred years, we believe that ozone was roughly similar to it as it is today. We want to divide this talk, or really focus our listeners here on the really 2 areas of ozone. The ozone that's in the stratosphere and the ozone that's in the troposphere. Those are both data sets that are in the Copernicus data store and often serve very different purposes. So on the left here, we're looking at a vertical profile of ozone in the atmosphere, and what you can see is that as you go up in the atmosphere, say around 20 kilometers for the South Pole, ozone is reaching its peak. And at lower down in the atmosphere, if you look on the right, because of various pollutants and disturbances to the atmosphere, you can get increased ozone down in the troposphere as well. So we are going to highlight those 2 because they're very important to human life, to ecosystems, and to a lot of the research that's going on. So stratospheric ozone, just to give the basics again, here is fairly high above the surface of the Earth and serves as an important protection from harmful UV radiation. And the stratospheric ozone has been seen to decrease due to human-produced chemicals, and we'll get to that in some more detail a little later. The causes of stratospheric ozone are somewhat understood, but we continue to learn about it as we go forward. I'm showing a spectrum of the radiation that comes from the sun. The dark gray area is what the radiation at the top of the atmosphere looks like, and we're looking at UV radiation and all of the radiation from the sun in the colored bands underneath. So much of the sun's radiation is blocked by the atmosphere, and in particular UV is fairly well blocked, but one of the main blockers for the very short wavelength UV radiation is ozone. In the troposphere, the sources of ozone are somewhat different. Although it's still the same chemical, it's still O3, And it's important because it can be harmful to human health, to ecosystems, and to structures at the surface. But that isn't the only reason we study tropospheric ozone. It gives us a lot of insights into how the atmosphere as a whole is behaving and where different trace chemicals, including ozone, are going from and going to. So tropospheric ozone has been increasing over the last 180 years or so. The estimates of how much it's been increasing vary quite a bit, but we do understand that it's an irritant and it has very regional as well as widespread effects. So I'd like to now switch over to how we measure ozone. For that, Martine, would you like to take over?
Yes, thank you, Betsy. So I will now go a little bit more into details of how we measure ozone and how we know all the facts that we know about ozone today. Next slide, please. So today, of course, we have a lot of observations from satellites, especially since the International Geophysical Year. We know that the atmosphere is much observed by satellites, and of course they have the big advantage that they provide us with a global coverage. And we have a global view on the ozone concentrations and distributions and variability above the Earth. And so you might wonder, why do we need these in situ observations, and why are we so much focusing still on the ground-based observations? Well, the problem is, of course, that the satellites, they have a limited lifetime per satellite instrument, typically 5 to 10 years. And as they are in space, they are subject to high energy radiation, essentially the UV that Betsy talked about, that is not reaching the Earth's surface, but that is present in the higher atmosphere and in the space. And so these satellite instruments, which are mainly optical instruments, they are subject to degradation of the optics. And as they are in space, of course, it's difficult to diagnose, to detect, and to repair. Also, the satellites have a very long lead time before they are launched, so it's not always the latest technology, and it's a very costly measurement. And a very essential question then is, how do you validate these satellites? How do you observe this degradation? And how do you fill gaps between data series from successive satellites? And if you have gaps between satellite series, if you want to create climate records, this will be really harmful to make homogeneous long-term records. So that's why there is still such a big interest in the ground-based observations. Now, these ground-based observations started before the satellite, of course. They started since 1920. They are local measurements, but as we deploy them in networks configurations, this alleviates to some extent the disadvantage that we have only local measurements. If we exploit the whole network of instruments and ground-based observations, we still have some kind of quasi-global coverage. And the ground-based measurements are, of course, much more sustainable. You can regularly maintain and repair your instruments, avoid degradation. It's less costly, and you can implement it much faster. You can always keep your instruments state-of-the-art and according to new technologies. So we have to keep in mind, and that's the message, the ground-based data really serve as reference data for the satellite measurements and the models. They serve as a transfer standard between successive satellite data series, and they offer more easily maybe the capability to provide reference, long-term and homogeneous, high-quality climate data records. That's why we submit them to the Copernicus Climate Data Store. Next. So this is today's, let's say, global ozone observing system. It's an integrated system, including, as I mentioned before, the satellites, the ground-based data, and in between you also have some aircraft measurements or some balloon measurements to cover the whole atmosphere and the whole vertical range of the atmosphere. A very important part is then the calibration and the quality assurance of all these data. And there are specific campaigns and activities focusing on these calibration and quality assurance efforts, for example, in the context of the Global Atmosphere Watch program. After these data are nicely calibrated and characterized, they go to the World Data Centers like the WOODS, the World Ozone and UV Data Center, the NDAC that was already mentioned. And then they can be used for global atmospheric reanalysis to produce also support the creation of homogenized satellite ozone data products and to vary all the user applications, scientific assessments of the ozone behavior, and the topics that Betsy mentioned, health and air quality assessments, forecasts of ozone depletion, and so on. Next. Yeah, and so some of these data, we submit them to the CDS after really careful characterization and making sure that we have long-term observational records. So in the reference ozone data that are today available in the Climate Data Store, we have in situ data and remote sensing data. And I will start with the in situ data, which for the moment are the ozone sonde data. And this is the network of ozone sonde stations covering the whole world, as you can see, that are submitted. Well, a selection of them has been submitted to the CDS after making sure that the data that we have submitted are really carefully characterized and calibrated. But you see that we have a nice global coverage. Next. So how does I want to insist a little bit on how an ozone sonde observation works to let you understand what are really the challenges that we meet with this kind of data and what's the efforts that are needed to make these data really reliable and homogeneous. So as you know, probably an ozone sonde observation, it's a sonde launched with a small balloon that goes up to about 30 to 35 kilometer altitude in the atmosphere, and that will provide data with a vertical resolution of the order of 100 to 150 meters. The ozone sonde itself is an electrochemical concentration cell, and together with the ozone sonde, we generally also launch radio sondes to have the environmental parameters that go with the ozone measurements. The environmental parameters and the sonde parameters, for example, the ozone sensor current, the pump temperature, and so on. Next. So the principle of this electrochemical cell measurement is that the ozone measurement is based on the titration of ozone in a potassium iodide sensing solution according to the reaction that is on the slide. And each molecule in that cell causes 2 electrons to flow in an electrical circuit. And so the final product, the partial pressure of ozone, is given by the formula that you see on the slide. And what is important in this formula is, so it's essentially, the ozone partial pressure is essentially proportional to the current that you measure in the circuit. But there is some constants that you have to take into account related to the quality of the ozone cell, to the preparation of the cell, to the pressure in the cell, and so on. And so it's very important to characterize these parameters to have a correct measurement of your ozone. And that's where all the challenges come in, to know these parameters, to follow them, to characterize them while you are preparing the sonde and during the flight. Next. So this is just a picture of the preparation of such an ozone sonde launch, where you see all the work to be done in the lab to prepare the sonde, to measure these characteristics and to note them down for further reference. And so it's very important for the traceability of the measurements afterwards that you keep account of all these parameters that may impact your accuracy of your ozone measurement. And these have to be submitted as metadata to be able to afterwards really trace back what the measurement is the value of the measurement. Next, please. So the importance of the traceability is something that I want to stress. Next. This is just an example of some ozone vertical profile soundings in different environments, in the tropics, in the South Pole, but I will not insist on that. Next, please. Next to the in situ data, we have also remote sensing data in the climate data store. And the ones that we have submitted up to now, yeah, just I want to remind you the principle of remote sensing. As Betsy has already shown, the upper curve is the solar radiation coming into the atmosphere. It's essentially the a Planck curve of the corresponding to the temperature of the sun. And another radiation that we have is the Earth's radiation in the farther infrared region. So the left curve on the right bubble on the curve, corresponding to the temperature of the Earth. And as this radiation is transferred to the atmosphere, to the ground, the different gases and species in the atmosphere absorb radiation in the UV visible, in the near infrared, and even further in the microwave region. Next. And these absorptions are due to the interaction between the molecule and the radiation that changes the energy of the molecule. When the far infrared and the microwave radiation changes correspond to changes in the rotational energy of the molecules. In the mid-infrared and the near-infrared, it's rather related to changes in the vibrational energy levels of the molecule. And for the still higher energy levels, UV and visible, it's the electronic energy levels that you are changing. Next. So for the ozone then in particular, this is, let's say, the radiation spectrum. We can measure ozone in the UV visible region. That's the Hartley and the Huggins band. Can you show them, Betsy? Yes. So we have ozone absorbing in the UV and in the visible. We have ozone absorbing in the infrared region. So we can also measure ozone in the infrared. That's the next spectrum that you can see here. And we can also measure ozone in the microwave region. So we have plenty of absorption lines that we can use to detect ozone, and these correspond to different instruments that measure these ozone concentrations in the atmosphere. Next slide. So this is, let's say, the current suite of ground-based type instruments that we use to detect ozone, each measuring in a different spectral region, as I have shown before. And in addition, we have the LiDAR measurements, which make use of active remote sensing. It means that you don't use the sun or the Earth's radiation of the atmosphere as the source, but yet you use an active a laser source, in this case, to probe the atmosphere. Next. So remote sensing measurements, opposite to the in situ measurements, they don't sample the air locally. They do a measurement by remotely. And so the direct signal is a kind of spectrum, and you need an inversion algorithm to convert that measured signal into the geophysical information, which is the ozone concentrations. So on top of the instrumental challenges that I showed for the ozone sonde measurements, here you have still some additional challenges with your algorithms. Using different algorithms may lead to different ozone concentration results from the same instrument and from the same spectrum. So that's an additional challenge that we have with the remote sensing measurements. Next, please. So I want to highlight the Dobson spectrometer. That's one of these instruments that measure ozone in the UV visible range. It's the first dedicated ground-based remote sensing instrument that was introduced by Dobson in 1924. The principle of the Dobson spectrometer, next slide please, is that you measure differences. So you measure a pair of wavelengths, two different wavelengths separated by about 20 nanometers with different absorption strengths, and by making the difference between these two intensities, I would say, you can derive the ozone concentration. It's a very high accuracy instrument. It has a good long-term stability. And so it's very much still the reference instrument today. Next slide, please. So the the Dobson instrument is still a reference measurement, and the Dobson network has more than 100 stations worldwide today. It has the longest record of ozone measurements from the ground since 1924. In addition to the Dobson, we now also have the Brewer spectrometers. Next, please. So, yeah, one point that's important, the Dobson spectrometer is a very labor-intensive measurement up to now, but nowadays also automation of the Dobson instruments is ongoing to make it much more, much less costly and more easy to deploy. And in addition, the Brewer spectrophotometer has been introduced also as a reference standard instrument in the World Meteorological Organization Ozone Monitoring Network. And so in the CDS, we have data from the Dobson and the Brewer networks. Next, please. This is the whole network of Brewer and Dobson stations that we have submitted to the CDS climate data store. Next. So as I want to stress that if you want to derive climate data records from these ground-based instruments, ozone sondes or remote sensing instruments, the usability for climate monitoring really requires compliance with meteorological standards, in particular, a very good calibration stability. Next. And so as an example, for the Dobsons, there are really regular calibration exercises where a Dobson from one side is brought to a calibration center and compared to one of the standard Dobson instruments. These Dobson instruments are characterized by a number, and so there are primary and secondary standards, and every 2 years the primary standard is then itself calibrated against the sun at Mauna Loa Observatory. So this is a very important exercise to keep the whole network really consistent, well calibrated and highly accurate. And on the next slide, you can see the result of these exercises. So this is a slide showing the success of the global Dobson calibration network until 2020, where you see that so these show the differences between a Dobson instrument and the reference standard Dobson instrument. And you see that in the course of time, the Dobsons come always closer and closer to the standard. So the differences get now, if you look in 2020, we are within plus or minus 1% for the whole Dobson network, which is an incredibly good result. Next, please. So I have shown in detail the ozone sonde, the Dobson and the Brewers, but of course I also mentioned these other types of remote sensing instruments, and it's very important that we have these different ozone data sets because they are complementary. They are deployed at different locations, and each of these instruments has a different temporal coverage depending on the characteristics of the measurement. And they have a different vertical information content. Some measure only the total column, others measure partial columns, others measure really a vertical profile with a high vertical resolution. So merging the data sets from all these different instruments is challenging and not necessarily desirable, but using them all together is very important and very useful. But to make this combined use, it requires the data quality protocols to be controlled, compliance with metrology standards, a good consistency within one network of similar instruments, and also a good consistency across different networks, across different instruments. And so this is why we do regular intercomparison campaigns between different instruments and why we have also developed the concept of the traveling standards. Next. So just an example of a recent paper that we are preparing about intercomparisons between ozone climate data records at Loader, where we have all these different instruments together collocated at one site, FTIR, UMKER, microwave radiometer, LiDAR, and sondes, and where you see here in the table a little bit the different characteristics of these instruments. Next. Where we compare the different time series for ozone. at this site from the different instruments. Next. And where you see also in the vertical range, if you compare these different instruments, that there are still some differences with respect to each other. And so it's really important that we understand these differences and that we try to minimize them to, in the end, be able to make combined use of all the data. The traveling standard concept is also very important today because many of these instruments have been deployed at fixed locations. And if you want to really make sure that your network is consistent, it's very useful to characterize the instrument at one location very well and compare it, for example, with in situ measurements, and then have a compact instrument that you can move from one observatory to another to make sure that all the observatories measure exactly the same ozone quantity if you have the same conditions. Next slide, please. So that was what I wanted to tell about ozone measurements. Now I want to show a little bit how these ground-based observations are useful to characterize the ozone variability and the changes. So ozone variability, ozone in the atmosphere is very variable in space and time. This is just a plot to show taken at one place in Uccle in the year 2009, the Brewer total column ozone as a function of the year. And you see the high variability from day to day. That's what we call the synoptic variability, which has much to do with the transport and the meteorological situation. Next, if you go to the global scale, on the left-hand side, you see a contour plot of the total ozone as a function of latitude, the vertical axis, and as a function of time, the horizontal axis. And you see that the two hemispheres are not completely symmetrical. That's one observation that you can make. You see that there is quite some seasonal variation, but much less at the tropics. The right-hand side figure gives you a cross-section for different latitudes. So a horizontal cross-section through the contour plot to show better the seasonal variation and the difference also in total ozone concentration at the different latitudes. Next. And so what happened in 1985? Suddenly there was a paper coming out from the total ozone measurements that had been carried on in Antarctica at Halley Bay Observatory, where they saw, luckily they had been doing these continuous ozone measurements since 1950, and then they saw in the beginning of the years 1980 that the October measurements of total column ozone decreased dramatically. That was the, let's say, the first warning against the ozone loss that we have experienced in the 1980s. Next, please. Yeah, this is just a similar plot where you see the ozone decrease in 1995 and 1997 compared to the mean ozone values that were observed in the period before 1972. Next. So what was the origin of this phenomenon? Man-made, long-lived halogenated and brominated gases, which we call today the ozone-depleting substances, they have caused these severe chemical ozone losses observed since 1980. And they were not limited to the polar regions or to the Antarctic. They have been observed, well, ozone loss has been observed at the global level. And theories have been developed explaining these ozone losses by catalytic gas phase chemistry and also heterogeneous chemistry. And so that these theories have enabled to understand the problem and the threat of these ozone depleting substances for mankind and life on Earth. And these are the pictures of the three main actors in this development of these theories, which are Rowland, Molina, and Crutzen, who got the Nobel Prize for their discoveries in 1995. And so after these discoveries, we went to international policies have been established, the Montreal Protocol, to enable mitigation of the problem, and Betsy will go further into that later on. And they have mitigated to some extent this ozone depletion, but now it's very important to continue to monitor the decrease of these ozone depleting substances and to monitor the associated ozone recovery that we are aiming at. And that's what I'm going to show in the next slides. So where are we today? This is the observed total column ozone trend in blue. So it's as a function of latitude. On the vertical axis, you see the trend in percentage per decade. The blue line gives you the median of the trend before 1995, and the red gives you the trends observed since 1996 up to 2020. And these trend estimates are made based on data from satellites, but also including the WOODS data sets, so these ground-based observations that I mentioned before. And you see that, well, these trend analysis require statistical regression methods and sophisticated trend models. Here we have used a linear trend model and multilinear regression techniques, which account for the known impacts of changes in aerosol, natural cycles, and dynamics to really sort out the trend due to the ozone depleting substances. So to really get here the trends due to the chemical ozone loss processes. And you see that now in the recovery period, we have very small trends. It's of the order of 1 to 2%, 0 in the tropics, and barely significant in the Northern Hemisphere. But they can be explained by the trends that we currently observe in the ozone depleting substances or the equivalent effective stratospheric chlorine. And so I want to stress here these small trends, 1 to 2%. I mentioned before the Dobson calibration within 1%. So you see the importance of having these ground-based observations very accurate and very precise. Otherwise, we would not be able to detect these kind of small trends. Next slide, please. This shows the observed vertical trends in the vertical profile. And here I show a picture where we have 3 different stations with different instruments, ground-based instruments, showing from each of these instruments, and I will not go into the details, but just showing how the different ground-based instruments quite well agree when it comes to detecting the trends. Of course, there are uncertainties and there are still some discrepancies, but you see a very nice use of these ground-based data to detect the vertical profile trends. And it's important to have the vertical profile trends to understand the processes. The processes are much less clear from the total column trends, but become more clear from the vertical profile trends. And you see that we have significant positive trends in the upper stratosphere for nearly all the data sets. The lower stratospheric picture is still a little bit blurred because the consistency between the data is not good enough to really figure out for the moment what is the exact trend. And so we suspect still some inhomogeneities in the different measurement time series that are not yet properly considered. Again, stressing the need for data curation, for improving the data accuracy, and so on. Next. If we go to the future, but maybe I should speed a little bit up. These are the projected total column ozone trends from models. And what is important here to show is if you go to the future, the different colored lines, these are the trends made under different scenarios for greenhouse gas emissions in the future and for what is called the socio-economic pathways. And you see that there's still a lot of uncertainty in the ozone recovery for the future, depending on which scenario you follow for the greenhouse gas emissions. So the evolution of climate has a very strong link with the evolution of ozone in the future. The near global total column ozone is not projected to return to mid-late 20th century levels under the scenario with the strongest greenhouse gas and near-term climate forces mitigation. That's the blue and the and the magenta lines that you see that remain below the reference level drawn in the figure. Next, please. Yeah, this is a similar picture, but separated among different latitude bands, where you see that depending on the latitude band, the projected ozone trends can also be quite different. For example, in the tropical regions, you see that we hardly recover, but you also see that the trends are very much smaller. Be careful, because the vertical axis for the total columns are different in the three plots. Next slide, please. One other point that is important to mention, and Betsy mentioned already at the beginning, the tropospheric ozone. We should not forget about that, because there's also a trend in the tropospheric ozone, which is due to very different reasons. It's due to the changes in the air quality pollutants in the VOx and in the volatile organic compounds and in the nitrogen oxides. And so we have also trends in the tropospheric ozone column that you see here for different scenarios, again, for different socioeconomic pathways. And these, of course, come into play when you consider the total ozone column trends, because even if the tropospheric column is only 10% of the total column, if the tropospheric ozone is increasing, it will impact your global picture of the total column evolution. Next slide, please. And then just one word about the polar ozone trend, because I started off with the Antarctic ozone hole. So let's look at what the Antarctic ozone hole is doing today. It's the right-hand side pictures in September at the top and in October at the bottom for the Antarctic. So you see the evolution before let's say the year 2000, and the evolution after the year 2000. And you see that in the September data, we start seeing a little bit improvement of the total ozone. So also the Antarctic is probably to some extent recovering from the Antarctic ozone hole, but it's really very minor, and still the evolution is not completely sure. In the Arctic, that's the left-hand side picture, it's much more difficult to talk about a hole, and there's such a big variability that it's still very difficult to see whether there is a trend or not. It's still within the uncertainties, as you can see the numbers on the top. Next, please. So roughly speaking, we can say that the ozone decline has stopped. The ozone hole size is currently more determined by temperature and dynamics than by the ozone depleting substances. At least there is no evidence of worsening, and how it will continue has to be monitored. The return to the pre-depletion levels will likely be mid-century, but as I said, climate change will impact the recovery rate, and we cannot predict. Well, there's still a big uncertainty on what will be the date of the recovery and what will be the level of the recovery, because there is some indications for a super recovery at some latitudes, also depending on the evolution of climate change. Next. Betsy, maybe you want to comment on this slide. It's the maximum yearly ozone hole content. You see that the ozone hole has increased in size in the years 1990. And now I think this increase has been stabilized, and we are going, in the last years, we might see slowly a reduction of the ozone hole size, well, the surface area.
One of the points that I want to make with this is that as we talk about ozone recovery, there are so many different ways we can discuss it. We can talk about what's the worst ozone hole. We can talk about the area of the ozone hole. We can talk about how long the ozone hole lasted, how many days it lasted. We can talk about the total net depletion of ozone throughout the whole. And that's just talking about the Antarctic. When we're talking about mid-latitude ozone hole, as Martine was saying, or mid-latitude ozone loss, we have other ways to describe it. So there is no single way that we describe ozone recovery. As scientists, we're looking at a lot of different metrics, And then if we care about the impacts due to the ozone loss, that can determine which way we actually try to quantify how much is lost. If we care about phytoplankton, we might care about how many days we have excessive UV radiation. If we care about human health, we may care about a different metric for mid-latitudes. So similarly, looking at the ozone hole as we just were, we could also be looking at how long the ozone hole lasted. And this plot shows for a few different years, 1920, 21, and 22, you can see how in general, the ozone levels were below average in October, November, and December, even when the average is compared to the last, say, 40 years of data. So trying to understand whether or not the ozone layer is getting better because the ozone hole doesn't seem to cover as much area might not be as useful as taking a look at some of these other metrics for recovery. So
I
again,
can skip this slide, Betsy.
okay, great. Then I'll take over talking about the international legislation. And I think I'm lucky to be able to talk about this because this is one of our real success stories as scientists and really as in terms of citizens of the earth in this day of globalization. So I'd like to really approach this from the scientific perspective, and I'll be repeating a little bit of what Martine said, but I want to start with the idea that we might have ozone loss really started in the 1970s. So the theory behind the ozone loss that came from Paul Crutzen, Mario Molina, and Sherry Rowland predated our observations of the ozone loss. Okay, the theory wasn't as full as it was, as it is developed now, but all the seeds were there. And then in the 1980s, as Martine said, we started to see the ozone loss in Antarctica. The first observations came from the Japanese, who observed the ozone variability and the strong causes. And then we saw that this was associated with chlorine. It was also confirmed by satellite. But I do want to make one mention that the very first observations of the low ozone values, for at least some of the instruments, particularly the satellite instruments, were identified as being erroneous data because they weren't recognized as being within the norms. So we need to take care with our data from that perspective, and that's one of the reasons why in situ and ground-based observations are so important. In the 1980s, as soon as the systematic loss was identified, there was also confirmation of chlorine as being one of the key culprits there, confirming what the original theories had produced. Throughout the 1990s, we continued our understanding of the Earth system. Additional chemicals have been identified and added on to what needed to be included under the international agreements. We got a better understanding of the role of aerosols. We started observing ozone loss, chaotic as it is, less systematic in the Arctic than it is in the Antarctic. And we developed a wide variety of analysis techniques, both for intercomparing the observation systems, as Martine was saying, but also for how we analyze the data and how we account for the other factors. And then, of course, this was beautifully topped off in 1995 with the Nobel Prize being delivered for this effort. But the international agreement, I think, really is founded on the scientific cooperation, collaboration, and joint work that brought all of the understanding together, the theoretical as well as the observational work together into one umbrella. It also was very helpful that it was done in an international way with scientists from Asia, from Europe, and from the US, all contributing to making sure that we were observing things correctly and understanding those observations appropriately. So this led to what's now summarized often as just the Montreal Protocol and the Montreal Protocol and its amendments. I think it's important to understand that the original effort was looking at us having potentially a large increase in ozone depleting substances. That's this no protocol pathway. And then when the Montreal Protocol first came into effect, it was going to limit how much we were going to see in terms of effective fluorine in the stratosphere, but it really wasn't going to be successful on its own. As we learned more, as we developed better understanding of the ozone layer, we added on additional amendments, the London Amendment, the Copenhagen Amendment, etc. And each of these brought our understanding up to date, and the international agreements therefore reflected our understanding, and additional efforts were put into place to protect the ozone layer. I want to give this bit of a timeline for the Montreal Protocol, if you can see these years spread out here. So again, the Vienna Convention predated the Montreal Protocol. That's where we set up our ideas as to how the Montreal Protocol should work. We quickly in the 90s added on the additional amendments. And then quite important, we saw a peak in the ozone depleting substances in the late 1990s, but we weren't done yet. We continued to look for continued confirmation of our understanding and refinement of our understanding. I think it was a really wonderful thing that we had universal ratification in 2009. Meaning all 196 parties had signed on to the Montreal Protocol. That's just got to be about as impressive as it comes. We saw the peak of fluorine, ozone depleting substances in the late 1990s, and then the Kigali Amendment in 2016 to be put into effect in 2019 became, I think, an additional incredibly important adjustment to this international agreement, and I'd like to spend a moment to talk about that. But I want to put this all into perspective of what fluorine was doing, what effective fluorine was doing. So ozone depleting substances, while we were on this timeline of understanding things in the 1970s with the theory coming into place and the observations in the mid 80s, and then continuation of our improvement of understanding in our international legislation. Meanwhile, the effective emissions, or the emissions of halogens, were building up from the 1960s on. So this was an interesting situation of, we had almost a slow burning, a slow erupting problem occurring in the atmosphere. I think we can be proud of catching it early. That earlier plot that I showed you indicated where we would have gotten to if we had not caught this early. But it also shows that, that we had something going on kind of underneath our noses, and it took an awful lot of effort to catch it as we did. As we look at the future scenarios, well, as I indicated, our equivalent effective stratospheric fluorine has peaked, and now we are looking for the signs of ozone recovery as we go forward. But as Martine already indicated, what type of recovery we're looking at really depends on how much the stratosphere is going to cool. As we get a warming from increased greenhouse gases, that actually results in a cooling in the stratosphere. And for most parts of the Earth, the cooling in the stratosphere really tips the production versus destruction of ozone over into the production area. So this would be the super recovery that we're looking at, potentially seen near the end of the century. So if we have a really unmitigated growth in greenhouse gases, we may end up seeing a super recovery of ozone, and that is not necessarily a good thing. The world has existed for billions of years with similar ozone and therefore similar UV levels. It's not clear that what we want is anything above or significantly different from what we've had in the past. So we need the observations and the accuracy of the observations to be able to watch what we're doing with the ozone layer. And when I say what we're doing, or what we're inadvertently doing, and again, what we're talking about is just a few percentages difference. So we need to be able to be monitoring at the ability to detect that. But I don't think we should ever forget that the Montreal Protocol serves as an example of a successful process. And I reached out to quite a few of my colleagues over the last 2 months in preparation for this talk to ask why they thought it was so successful, each of them having been involved from a different perspective. And some of the themes that kept coming forward were that it was a flexible effort, meaning that it wasn't too ambitious at the start, and it also got amended and amended as we learned more. There was regular information via scientific updates. Some of you may be aware that we have an ozone assessment every 4 years, and it's absolutely impressive the quality of the work that goes into those ozone assessments, as well as the regularity. They are coming out like clockwork, but in addition, when it's necessary to have an extra assessment to address specific issues, that is also arranged for. There was a respectful treatment of developing and developed countries, recognizing that not all countries were able to make the changes in a similar manner. And there were coordinated observations of ozone, ozone depleting substances, and UV radiation. While that wasn't, those coordinated observations were not all dictated by the international agreements, the scientific community stepped forward and almost self-identified in some cases what we needed, and with each country, each laboratory doing what they could to bring it forward. I also want to say that the Montreal Protocol, as early as it was in the entire international environmental agreements range, it was already promoting sustainable development goals that are now codified by the UN. I think that that's impressive, that it was designed in such a way that it was respectful of poverty, of hunger, of good health, of well-being, etc. So there's just an awful lot of thoughtfulness that went into it, and yet it didn't bog down the process in a way that it wasn't able to be effective. So I think there's just a lot to learn from it, and I'm going to ask Martine to share her thoughts on this as we get closer to the end. So again, I reached out to an awful lot of colleagues and asked them how and why we succeeded, with an eye towards our observations and what role did our observations play. And there are many people who have written beautifully on how the social aspect of the Montreal Protocol and how the negotiations occurred. I want to really stick to the concept of the science and how the observations helped us. And I really feel like the success was built on solid science, collaborative diplomacy, and worldwide support. But again, the risk was identified in the 1970s before we even saw the loss of the ozone. In the 1980s, we saw the ozone changes. In the 1990s, we were already phasing out and got to the peak of fluorine in the stratosphere. In the 2000s, we continue to present and refine our scientific understanding, and our knowledge does continue to grow. For anyone who wants to believe that ozone is a completely solved problem, I have a few additional updates that I'd like to share with you that indicate to me that it's a very active area of research, a very dynamic area with new results coming out all the time. But let's focus on the observations for a moment. Long-term baseline observations were absolutely critical. As Martine indicated, we started with Dobson measurements in 1924. If we didn't have that baseline information, it would have been more difficult to identify that these changes were real, significant changes that we were observing, not just in the Antarctic, where the changes were large, but also at mid-latitude. So baseline observations were critical. Redundancy from multiple international groups was important, and as Martine indicated, the intercomparisons that started occurring almost immediately and got refined and improved over the years helped our understanding of not just our instrumentation, but also of the Earth system. The vertical profiles continue to be critical for confirming the cause of our low total column ozone levels. And the satellites in combination with our ground base were critical for showing the physical extent of the ozone loss and the long-term changes. The intercomparison of observations showed great value, and the traceability to meteorological standards became valuable. I'm listing all of these off here, and I embrace tiered networks, meaning that not every observation needs to come from an extremely expensive, difficult to maintain observing system, that we can have high-level systems, mid-level systems, low-level systems, all complementing our ability to monitor the Earth. Almost, I would say every single one of these points is not just useful when it comes to ozone, in the monitoring of our ozone layer. But all of these are principles that we have now adapted, I believe, and taken over into other types of monitoring, including climate change. So we are looking for ozone recovery, including in the non-polar regions. Here we have it for at 19 kilometers above the surface and 42 kilometers above the surface. Again, stressing how important it is to look in the vertical. I want to say a few words about ozone and climate change to augment what Martine has already said. The original work on climate change and ozone depletion focused really on the direct impacts that the temperature affects ozone concentrations and therefore depletion mechanisms. Ozone is constantly made and destroyed, and those mechanisms are all temperature sensitive. And the original work also focused on the fact that ozone is a greenhouse gas. But in the last few decades, the complexity has been emerging that not just that both climate change and ozone levels contribute to changes in dynamics, and that affects everything from whether or not we have a cold winter to whether or not we stay in droughts longer. So we are still working to disentangle how climate change and ozone work together to impact the dynamics of the atmosphere. Many ozone depleting substances are powerful and potentially long-lived greenhouse gases. Stratospheric tropospheric change can influence surface ozone levels as well as stratospheric ozone levels. And here's an area that's really of active research right now. Fires, the aerosol emissions, but also the chemical reactions that take place downwind of fires are resulting in not just changes to air quality, but also decreases in total column ozone. And there have been a number of papers just in the last 12 months highlighting not only that this is happening, but this can be quite significant as we go forward. So work in these areas requires very, very careful, vertically resolved information. Again, many of the chemicals that we're talking about controlling and monitoring have both a strong influence on the ozone layer. So we're looking at ozone depleting potential on the left, but also have global warming potential, and that's on the right, with large influences on global warming potential. So you're seeing in the bottom part here, the HFCs, we're seeing a lot of the substitutes for CFC11, CFC12, etc., have almost no ozone depleting potential, and yet have a large global warming potential. And the HFCs are stable replacements, but HCFCs are also strong greenhouse gases. The Kigali Amendment to the Montreal Protocol is aimed at reducing these. And the impact of the Montreal Protocol, because it's reducing these chemicals that have greenhouse gas potential, might be considered 5 to 6 times larger than what we were trying to achieve with the Kyoto Protocol only about 10 years ago. Let me just show you a few details on this. What we're looking at is growth of HFCs into the future. And without the Montreal Protocol, they would have continued. But now with the Kigali Amendment, we're looking at reducing that. I want to go quickly and try to go within the next 5 minutes, finish up here. But there are a number of outstanding questions that we have, and this is why we need the data and why we need the data readily available in the Copernicus data store. So what we're looking at for stratospheric ozone data is, are the international treaties being upheld? And we saw within this last decade that, intentional or not, they weren't being fully upheld. And it was only by observing ozone depleting substances that we were able to understand that. I personally think our current network needs to be strengthened in order to make sure we have compliance when it comes to protecting the ozone layer. Are there any new chemicals that we need to be concerned with? We, as human beings, continue to produce new chemicals. I wouldn't say that we understand in advance exactly which ones are going to be harmful. Is the ozone layer recovering? And for the reasons we understand, Martine and I did our best to explain that the path of ozone is a complicated one, not just affected by ozone depleting substances and temperature, but also dynamics, aerosols, fires, volcanic eruptions, etc. Are there side effects due to the chemicals associated with ozone depletion? They might have to do with climate or the environment more generally. How will climate change affect the ozone layer? What are the impacts of future volcanic eruptions? We've seen it in the past. We're likely to see effusive volcanic eruptions in the future. As I told you, the wildfires are getting an enormous amount of interest because they're showing new chemical pathways, still involving fluorine, but we're still working on nailing that down. And here's a very important one for all of us to consider. If we need to address geoengineering for climate purposes, what will be the effect on ozone? If we have to do something drastic because the climate requires that, what will be the result, not just on ozone, but at UV at the surface? And what are the full set of impacts from elevated ultraviolet radiation? Right now, it's as if the Earth is under a grand experiment, and we're learning a lot in terms of that grand experiment. Tropospheric ozone, we have a number of questions also. I'm going to just whip through these as quickly as I can. How much is tropospheric ozone's increase due to local, regional, or global factors? That has everything to do with how we're going to be able to minimize it and protect human health. How does the changing troposphere affect climate? What are the full set of impacts, agriculture, ecosystems, and structures? Human health is often our driving issue here, and whatever we can do to protect human health is important. And what are the combined impacts of not just tropospheric ozone, but other stressors, including aerosol, temperature, and humidity? And what style of regulation, once our science is in a strong enough place, what style of regulation is the most effective? I'm going to skip through this and just point out that there's an awful lot of work going on in ultraviolet radiation. From in vitro, really doing things in a petri dish, to in vivo, looking at how UV affects actual living organisms, to looking at combined stressors, to looking at population impacts, and then looking at covariation, because often when UV is high, we have temperature being high and other factors being high. So with UV impacts, we're looking at plastics, we're looking at biogeochemical cycles in land and in water. I can say that there's a lot of interesting UV work going on, looking at what's happening with our oceans, ecosystems, and agriculture. Human health continues to be very important, with skin cancer still on the rise in some areas of the world and decreasing in other areas of the world. But this is one that I'm not sure if everyone is aware of. Immune suppression is raising its head again as a very important factor for UV radiation. And in particular, we now know much more, and there have been quite a few papers published about how COVID is affected by UV radiation. And there are multiple pathways there, how it helps with our immune system, and also how it kills COVID, and how that can be used dynamically. And then there's vitamin D, where we are seeing many parts of the world with populations, over half the population with low vitamin D levels. So as we're doing this experiment on the Earth, it makes all the sense that we make the most of this and try to understand so that we can give the best information going forward. I'm almost done here. Lessons learned, I think you've heard it through Martine's and my presentations, but we succeeded in part because the observation records were clear and the observations continued to improve and substantiate and refine our understanding. There was scientific understanding was sound, and the communication between scientists, public, and policymakers was direct, partly through the assessments that we did. I'm going to skip this slide because I'm repeating some of what I've already said. Baseline observations are absolutely golden. Open access to data like the Copernicus data store, accuracy, continuity, and stability. So I'd like to just hit our conclusions, which is that the role of science in identifying the issues with ozone, working with policymakers, is something we can all be proud of. Many scientific lessons we can learn, both small and large. Observations need to be trustworthy. That is not a trivial issue, especially when you're trying to get something that stays within 1% accuracy over decades. Working across scientific disciplines to identify the perils, designing observing systems fit for purpose, and continuing to refine science and inform policy is what our science community has done. We can all be proud of it. There's a lot more information out there that's available. And finally, we'd like to thank our colleagues who helped us develop some of the messages presented here, as well as all colleagues who have worked on the observations. With that, I'd like to ask Martine if she has any other take-home messages she'd like to say in terms of what we as a community have learned from this grand effort in ozone observing.
Well, thank you, Betsy. Maybe just an additional comment. The Montreal Protocol has been a great success, as you highlighted and as you have demonstrated. And I think the approach taken in the implementation of the Montreal Protocol, where you have meetings with the scientists and the research managers and the policy makers on one hand, then the scientific assessments of the ozone, state of the ozone, and the successive adjustments of the Montreal Protocol. This methodology or this approach has to some extent been transferred to the climate change issue. The IPCC reports started about 5 to 10 years later than we had with the ozone reports. But it's a similar process. You have meetings of the scientists, you have communication to the policymakers, implementation of regulations, and this interplay is very important. And I think the success of the Montreal Protocol has guided also to some extent the efforts taken to mitigate climate change. And I think that's another demonstration of the success of this approach that was, I would say, initiated with the ozone depletion topic.
Thank you, Martine. Monica, do we have questions? I'm not able to see the chat.
Yes, thank you. Thank you, Betsy and Martine, for your so clear presentation. And okay, yes, there are some questions. I'm sharing my screen so you can see. Just a moment. Okay. Can you see? No?
Not yet.
Pietro, can you give me?
While you're working on that, Martine, I'll just comment that you and I are both aware that a lot of the same people involved in the ozone assessments also worked with IPCC. So it's not completely surprising that there's been that crossover. But when it comes to the fundamental observations, the observations of ozone, which you're so grand at coordinating globally, do you feel like there's that same communication between folks who are involved in the observations for ozone as the observations for climate change? Are the lessons being passed back and forth between the ozone and climate change observing communities?
Yes, I think so, because as you say, it's much the same community. Many people are involved in both, and international global networks like NDAC or CRUAN, they not only address ozone, they also address some of these other species. So the issues of meteorological standards and characterization, traceability, they are also, and even more, I would say, important or as important for climate change monitoring. And so they are, yeah, the knowledge about how to do a good measurement, how to improve accuracy, how intercompare measurements is transferred from one community to the other. And I think it's really communicating efforts.
Okay. Okay, I think that you can see my screen. I've collected the main relevant questions. Can you hear me?
Yep.
I see the first question.
The first, it is, I think, to Martine, because it is related to the second part of your presentation. And how did you calibrate climate models such as Cordex? Okay, what method did you use? It is questions made by a participant with Al-Shibli.
Well, I think I cannot give a very precise answer, for example, for Cordex, but in general, what people do is that they compare the observations with model simulations to check the agreement between what the models predict or simulate and what the observations tell you. And if you see disagreements, you try to correct some of the processes in the models, the transport processes or the chemical processes. And once you have a good agreement between your climate model for, let's say, past and present, in agreement with your observations for the past and the present, then you can start extrapolating your climate models to the future, because you have confidence in the fact that your model will reproduce the current state of the atmosphere. And so then you can start using your climate model to forecast the future. So the observations mainly are used to check the agreement of your model simulations with your observations and to get trust, to get confidence in the models. I hope that answers the question.
Okay,
maybe
thank you,
Betsy, you
Martin.
have something that you want to add to that, but
Well, I do know that this is an area of continued interest, and that, for instance, in this latest ozone assessment, they used a slightly different approach to calibrate the models with the observations, allowing that there's some uncertainty even at the starting point. Sometimes they would sort of have them all bring themselves together in 1980 and then look at the deviation from 1980 or something like that. And this latest ozone assessment did something a little bit different. I think the details are in the assessment though. So I want to point out that it's an area of continued research, and as our models improve, we're able to calibrate even better. But one of the things that we should never forget is that, as Martine, you explained, is that none of these observations are perfect. They all have some level of uncertainty, and they all, whether they're doing a very broad area of the vertical or a finite area of the vertical, we need to make use of the strengths of the observations and match them appropriately with the models.
yeah, and maybe something I want to add to that. When you see a disagreement between your model simulation and your ozone observations, you have to try to find out why. Is it in the chemistry? Is it in the transport? So it's also very important to have other observations of other species to check with your models. For example, you could use measurements of nitrous oxide, which is a tracer, or of hydrogen fluoride, which is a tracer in the stratosphere, to check your the agreement between your model predictions of that tracer and your observations of that tracer, because then you have a good handle on knowing the accuracy of the transport model, the transport module in your model. So it's not only important to calibrate the climate models only with ozone concentrations, but also with other kind of observations to check the different drivers that are in your climate model. So as Betsy said, different ozone measurements have their complementarity, but you also have complementarity with other species that impact your models. So you need a whole suite of observations, in fact, to calibrate your climate model, not only ozone concentrations.
Okay, thank you, Martin and Betsy. The second question is that I was interested to explore tropospheric ozone data from Sentinel-5. TROPOME satellite instrument over Pakistan, but I later know the data is available only 20 north to 20 south. What it is? Any specific reason? This is questions written by Suhaib Malik.
I do not know the answer to that.
I was not aware that it's only available 20 north to 20 south, and so I don't know exactly the reason either. But what I can imagine is that tropospheric ozone is not a direct product from Sentinel-5 TROPOME. The direct product is the total column. And so to derive the tropospheric ozone, you need to apply differential methods and residual methods. There are different methods to derive the tropospheric ozone. And so maybe these methods have not the necessary inputs in the other regions. outside of the tropics or over Pakistan. That's one reason that I can imagine, but I'm not sure. It's just a guess. But it's sure that tropospheric ozone is not a direct product from tropominy. It needs some additional data and some additional algorithms, and that's maybe where the point is, to get it also reliable outside of this 20 north to 20 south latitude band. But I can check if you leave an email address, we can try to answer the question more precisely.
Okay, thank you, Martin. And okay, just a last check to the questions if there are any.
I'd be happy to, while you're looking for more questions or waiting for someone to type something in, I can share one of the issues that Martins and my colleagues are very concerned with, and perhaps everyone who's listened to this webinar so far can understand themselves now, is that we have been monitoring the vertical profile of ozone to some extent with our MLS satellite. And we are concerned as a community, we're concerned that once that satellite, which is near the end of its life, is gone, that there are no current plans for follow-on, that we will lose that capability to monitor the vertical structure of ozone on a global level. And that's a concerning issue for us as scientists. I know some groups are getting together to discuss how this can be addressed. That's an unfortunate bit. But I also want to share that I think we're in a really amazing time when it comes to Earth observations, in that there are so many different ways that we can now monitor. There are microsatellites, there are private companies willing to fund observations, there's coordination across the globe on these issues, that I think there's reason to be hopeful, as long as we in the scientific community can be clear about what we need and communicate it appropriately. Martin, you and I have not really talked about this directly. I know that you're aware of the same issue. Do you have thoughts on this?
Yeah, it's good that you bring up the point because it's an important point. I want to add that you are right. We have a lot of data available. We have satellite data, we have aircraft data, systematic ground-based observations, and so on. But there is still some, I would say, some kind of competition with other fields of environmental research, and budgets are limited, and so there's always some pressure on keeping the measurements going, keeping the standards high, because it requires a lot of efforts. And so on the one hand, everyone is convinced that these measurements are indispensable. But on the other hand, there's the budgetary issue, the resources. And so there's always also some pressure on these measurements. And in particular, well, that's one point. And the other point I want to make is we have a lot of satellite data, but there is currently a little bit, and MLS is one of the examples, the one that you mentioned, a lack of vertical profile sounders in the stratosphere from satellites. MLS is about the only one we have left at this moment. So if MLS disappears, we have almost no vertical profiling capability in space for ozone and other stratospheric species like the ozone depleting substances. So I think that's very important that the satellite agencies also recognize the need for the vertical profiling. Sometimes they are more looking at total columns, and that's enough. We know what is going on, but that's not true. We need this vertical aspect. As you explained, to understand the processes, the vertical information is very important. And so we are in a golden area of satellite observations, but most are looking at nadir, so providing us total column data, and much less are available for vertical profile information. And that's one of the reasons, of course, why MLS is so important for the moment, because it's about the only one.
Then Martin and Betsy, there is a comment I put here in this slide. This is from Florian Kerber, and I loved your diagram on the evolution of ozone on the different level of Montreal Treaty, no action, impacts or amendment. It would be good to use the graphical example to inform the climate change debate. There's a tendency to claim either success way prematurely, or people are very disappointed because progress is slow.
Yes, yes, thank you. And I wish I could claim credit for that plot, but that plot has been a part of our community for quite a while. We're very proud of that. We update it as we have new amendments to the Montreal Protocol, and it is very useful. But Florian, I feel like you've made two separate issues. One is that that's a great way to communicate, and thank you. Martine and I struggle with what is the best way to communicate, and it's good to know that that works. I think that with the climate community, they are using that. They're using other efforts. It's not always easy to know exactly what moves the needle, and so I welcome continued comments on what is helpful in communicating.
Yes, and I agree with you, and I had that after your webinar, I think that we should organize much more webinars such this. Because it opens our minds and let us more aware about the importance of the climate data and observations. So thank you for your presentation.
Thank you, Monica. And thank you to the audience also for having attended this webinar. And it was nice to have some interesting questions. Thanks very much.
Thank you. Thank you. Okay, so I think that we can close this session. Thank you all. And the webinar will be available at the C3S webpage, and I'll send all participants anyway the link. Thank you. Bye.
Thank you. Bye. Bye to all.
Martine, it's been a pleasure.
I don't find how I can leave.
I think if you just click on the red dot that closes the window. And Monica, I don't hear you any longer. Okay.
Bye.